polar equations.
Okay.
Various things that we can do when we have polar equations. First of all, let's just review. If we want the area of that curve, we're going to take the integral of the polar equation that is an equation of theta, and we're going to evaluate it from theta 1 to theta 2, and there's a 1/2 there. And the reason there's a 1/2 there is because if you have the area of a sector, let's take a quarter of a circle. The area of any sector of a circle is 1/2 theta r squared. As long as theta is in radians.
Okay.
And in case you ever forget this, well, imagine if we were talking about the entire circle. We know that the area of the entire circle is pi r squared. So if theta was 2 pi, which would what it would be if we had the whole circle, right? In other words, if you go around the whole way, that's 2 pi. In other words, that's in radians.
Okay.
So the area of the circle would be 1/2 times 2 pi times r squared, which is the same as pi r squared. So we know we have the proper formula.
Oh, okay. Okay.
In other words, whenever you have a formula like this, always make sure that it works for geometric shapes that you know what the area is. We know the area of a circle is pi r squared, so therefore the area of a sector, if it was a quarter circle, has to be 1/2 theta r squared. And by that reasoning, when you have the area of part of a sector like that, it's still 1/2 theta r squared, as long as theta is in radians.
Okay, that makes sense.
Interestingly enough, I was on the internet the other day and I was trying to find a good explanation for the difference between radians and degrees.
Okay.
Because I've read plenty of explanations in the past, but I'm not sure I still understand why calculus works in radians only and it doesn't work in degrees.
Oh, right, you mentioned it.
In other words, it's not quite the same as gallons to liters. There's something fundamentally different about radians and degrees than there is about gallons and liters. Gallons and liters are merely two different measurements of unit, but they're basically, once you come up with the ratio of gallons per liters, they're the same thing.
Right.
Well, that's not the same thing with radians and degrees. Even though the difference between radians and degrees is 180 over pi, or pi over 180,
right,
if you're converting one to another.
Right.
The fundamental difference is that degrees is not a number. Radians is a number.
Oh, okay.
And the example that they gave that's similar, which I'm still not sure I fully get. I don't think it's similar, but they said the difference between percent and decimals. If you have an equation that has percent in it, you can't solve it. The only way you can solve it is if you convert that percent to a number.
I see.
And that's what they said, is we can't solve equations unless we have numbers. We can't solve equations with percent. We can't solve equations with degrees, because degrees is not a number. A degree is 1 over 360th of a circle, but it's not a number.
I see.
And so that's why calculus, that didn't satisfy me much either. At some point I'm going to understand that, but I still don't yet. But when you're finding the area of a sector, you want it in radians. It's not that you can't handle it in degrees. You can. In other words, if theta is in degrees, then you have to multiply this whole thing by pi over 180. In other words, if area is in degrees, then it's 1/2, and it's theta in degrees, but then times pi over 180 r squared. So that's what the area of a sector would be if it was in degrees. And again, notice that if theta is the full circle, it would be 360, which cancels out with the 360, and you end up with area equals pi r squared. So as long as these equations for the area of a sector agree with the area of a circle, we've got it right, whether we're in degrees or whether we're in radians.
Okay.
And that's pretty much the way to check whether you have it right or not, is just make sure, because the only thing that geometry teaches is what the area of a circle is. It doesn't teach the area of a sector, but this clearly works as long as theta is in radians. And of course, the question I don't know how to answer, but I've actually read an explanation of it, but I didn't understand it, and that is that calculus only works in radians. I mean, I read their explanation is that calculus needs numbers, not pieces of an angle. 103 or 1 over 360th of a circle. You got to have a number to do calculus, and that's what I don't quite understand. And it applies all the way to the fact that the derivative of sine is cosine. That would not be true if you were in degrees. It's only true if you're in radians.
Huh. No kidding. Wow.
Yeah. And I find that a little interesting in the sense that, well, first of all, I'm not sure you know this. Let's just look at it.
Okay.
There's the sine curve. Right below it is the cosine curve. And you'll notice that the derivative of sine is indeed cosine, based on slope.
Oh, I see.
In other words, the slope right there is 1. That's
Okay.
there.
Right.
The slope right there is 0. That's there.
Okay, right.
Slope right there is -1. That's right there. Slope right there is 0. That's right there. And finally you get back to the end and the slope is 1, and that's right there. So if I draw both curves, it's really easy to see why the derivative of sine is cosine. Just the slope at every single point is equal to the cosine value. I mean, it's almost amazing that that's true, but it is. But the thing is I don't know why that requires that to be 2 pi as opposed to 360 degrees. It doesn't seem like it should. In other words, it looks to me like even if we put degrees on this thing, the derivative of sine would still be cosine. What difference does it make if I label this thing 360 degrees as opposed to 2 pi? As long as I plot this curve directly under that curve, that can be 360 degrees, and the slope at every single point appears to be the value of cosine. And so the derivative of sine is cosine.
Yeah, couldn't you say like the sine of, 360 degrees equals what, and then it would just...
Well, I'm going to have to read my calc book that discusses this. And they actually give a full one-page explanation as to what would happen if you made stuff in degrees and why the derivative of sine would not be cosine. But I can't see it from this. From the picture I just drew, it looked like the derivative of sine would be cosine regardless of whether you're in radians or degrees.
Yeah, I see what you're saying completely.
Yeah. So I'm not sure about that, but I've got to believe what they're telling me. So anyway, based on this logic, that, in other words, if we take the area bounded by the two radial lines and the polar function, this is some function, f of theta equals r. That's what that function is. And we want to find that area. Then it's basically the summation of each of those sectors, which would be the summation of those. And given what we've been studying for the last 3 sessions, we know that the area under the curve is I going from 1 to n as the limit of this as n goes to infinity of some f of c sub I times delta theta. Only in this case it's the f of some theta sum. In other words, that's what we learned the limit definition was. And you can apply that limit definition to polar graphs just as easily as you can rectilinear graphs.
Okay.
Well, and this implies the integral, because the area of a sector is 1/2 theta r squared, then this implies that it's that. So we get the area, and I don't want to say under the curve because it's not really the area under the curve. It's the area defined or between the two radial lines and the curve. In other words, it's this area here. It's not this area here.
Oh, right, yeah.
Different than rectilinear.
Yeah.
Definitely between the radial lines. And that's a big concept in terms of doing these problems. Because as we've seen, when you have things like cardioids, in other words, we had a problem where we had a cardioid and a circle, and we were asked to find, I don't know what it was. It was the area, maybe it was the area between the two. I can't remember exactly. But it's a key concept knowing that if you're dealing with polar functions, the area is between the radial lines and the function.
Right. Yeah, I remember that. Now, when you put f of theta squared there, was that just in a case where the function was x squared or something? Or?
No, it's pi r squared. In other words, it's based on the summation of this. And r,
since f of theta is
r is f of theta. Okay. In other words, if I take one of these individual sectors that we're summing up, r is f of theta. So it's 1/2 theta times r squared, which turns into 1/2. The theta turns into delta theta, and the r squared turns into f of theta squared. Because f of theta is equal to r every time. In other words, the definition of this curve right there is defined by r, or f of theta.
Okay. Now, why does pi not make an appearance, though, in any of those? If it's based on the sector, you know what I mean?
Yeah, because the fact that we're in radians takes out the pi.
Okay.
In other words, since the measurement of theta is in radians, you still have a very good question, and I don't know the answer to it. Hold on. Yeah, you're right. It seems like we would have a pi. You think for a moment. We're summing up all of these sectors. That's what this does. Delta theta is the width of each sector, so to speak. Well, delta theta is the difference between alpha and beta. And we're summing up r squared times delta theta, which becomes this. Now, the one thing that my theorem says in my book is that beta minus alpha has to be less than or equal to 2 pi. So pi comes in there. And pi also is going to be involved in the measurement of alpha and beta.
Yeah, that's what I was thinking. Maybe that's what it is. That's where it shows up.
Right, that is where it shows up. In other words, if we were going between 30 and 60 degrees, we'd be going between pi over 6 would be alpha, pi over 3 would be beta, and when you do this integral and evaluate it, pi comes back into the picture.
Okay, that makes sense.
All right, let's see. Let me look. Did points of intersection. We did this problem here. All right, let's go on to the next section. We're going to figure out the arc length of a polar curve. In other words, we've figured out the area. That was fairly straightforward. But the arc length, in other words, the length of that arc from there to there, looks like, you know, we have no idea how to figure that out. My book kind of skips over the proof. Let's see, the formula for the length of a polar arc can be obtained from the arc length formula for a curve described by parametric equations.
Yeah, that's where I remember that we did something with that.
Yeah, it was fairly straightforward for parametric equations. In other words, it was the integral, and remember, we're always going from some angle to another angle. In other words, we're doing this d theta. So the length of the arc is the square root of f of theta squared plus f prime of theta squared, d theta.
Oh, I think I remember that, yeah.
Well, I don't know exactly how they got that. Don't explain it real well here. I'm trying to think of what the arc length of a rectangular. Oh, it was the arc length of parametric equations, not rectangular equations. And the arc length of parametric equations. I'd have to go back and look it up. But based on the formula for the arc length of parametric equations, and polar equations are parametric equations, even though it's r equals something in theta, that can be broken down into parametric equations.
Oh, now the formula you put up there, was that for rectilinear or parametric?
That's for polar.
Oh, this is for polar equation. Okay.
And it's basically the square root of f of theta squared plus f prime of theta squared, d theta.
Okay. Okay.
And they don't give much explanation for how they came up with that, other than to say that it can be derived from the same formula for parametric equations. Trying to think what the formula for parametric equations was. I thought the formula for parametric equations was dy dx squared plus dx dy or something squared. I don't know. But I don't want to back up that far at this point. So let's just kind of take this on principle that this is the formula for arc length, which is certainly something we might need to know. I mean, in terms of real life problems, the area under the polar curve and the arc length of the area and the surface area, if you took that polar equation and rotated it about one of the axes, what's the surface area of the figure that you get? All of those are things we need to know in terms of solving real-life problems. Well, this becomes from A to B the square root of r squared, which is f of theta squared, plus dr d theta squared. And of course there's a d theta outside. Let's do an example.
Wait, now this...
So all I did was equate this to that.
Okay, that's just the same thing.
Yeah, because r squared is the same as f of theta squared.
Oh, right.
And f prime of theta squared is the same as dr d theta squared.
Okay, I'm with you now.
Yeah. And the only thing we have to be careful about is when applying the arc length formula to a polar curve, be sure that the curve is traced out only once. Clearly that's going to make a difference. If we trace the curve out twice, we're going to get twice the length we should be getting.
Okay, only trace out the curve once. All right.
For example, they give one that is r equals cosine of 3 theta. If I were to try to find the arc length of that, it's important to understand that that's traced out once from 0 to pi, but traced out twice from 0 to 2 pi. So you can't assume that it's only traced out once when you go from 0 to 2 pi. You have to actually figure it out and know what traces these curves out exactly once. All right, let's do an example. Find the length of the arc from theta equals 0 to 2 pi for the cardioid that is the following. I kind of like the way they say this. R is equal to f of theta there's a cardioid function. Polar function that we call cardioid because it fits that a minus some other constant times cosine of theta. Whenever we see polar equations like that, we know they're cardioids, and they want the length of that cardioid, which looks like this.
And it was from what to what, was it?
Yeah. From 0 to 2 pi.
2 to 2 pi, okay.
Now, trying to figure out if we need to figure out whether that's traced out exactly once. Certainly when theta is 0, right there, well, that's 0. So that point is when theta is 0.
Okay.
When theta is pi over 2, this is the point. Because cosine of pi over 2 is 0. So this would be 2. When theta is pi, then this becomes minus 1, and this whole thing becomes 2 plus 2, which is that point. So I clearly haven't drawn it correctly. It needs to be drawn more like this. In other words, this horizontal distance right here is 4. And this is only 2. Okay. And so I traced out half of this cardioid going from 0 to pi. Clearly, the other half you get when you go from pi to 2 pi. So I can integrate this function from 0 to 2 pi and figure out the length of that arc, the length of that cardioid.
Say that again one more time, Dave.
I know that when I go from 0 to 2 pi, I trace this thing out exactly once.
Okay.
When I went from 0 to pi, I got this much of it.
Uh-huh.
So I think I can make the assumption that if I go from 0 to 2 pi, I get the rest of it, because it's symmetrical and all of that. But if I were to make up a table, you would see that as I go from 0 to 2 pi, I pick up points along the way, and I eventually get back to there.
Okay.
Okay. So this should be fairly straightforward. This should be equal to the integral from 0 to 2 pi, tracing it once, of r squared. Well, r is 2 minus 2 cosine theta. We've got to square that. Plus the derivative of that. Well, the derivative of that is, the derivative of cosine is minus sine. So the derivative of minus 2 cosine, in other words, the derivative of that is going to be 2 sine theta squared. That's what dr d theta is. In other words, I know what r is. Dr d theta is the derivative of this, which is 2 sine theta. So let me write this.
The second term is the derivative of the first term with respect to theta.
Well, the formula for arc length is r squared. Well, this is r. Plus r prime squared. Well, this is r prime. All d theta. So that's going to be the length of that cardioid. This is one that actually they've picked something that can be done without too much difficulty. Let me think for a second here. Well, let's see. If we do the math, what do we get? If I square that, I get 4 minus 8 cosine theta plus 4 cosine squared theta plus 4 sine squared theta. Just doing the algebra.
Okay.
Now, simplifying this thing, I can certainly factor out a 4. leaving 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. You with me?
Mm-hmm. Yeah.
Okay. And now that cosine squared theta plus sine squared theta is equal to 1. So now I have the square root of 4 times 2 minus 2 cosine theta, d theta. In other words, I'm going to replace that with a 1.
Okay.
And now they do something that's a little peculiar. They factor out a 2 from this expression,
Okay.
and they bring the entire 4 times 2 outside as a 2 root 2. In other words, if I factored another 2 out of here, I can make that 8, make that 1, make that 1. And then to take this 8 outside of the radical sign, it becomes 2 root 2.
Plus 1 minus 1 cosine. One sec here. So then you take the 8 out. How does the 8 become 2 root 2 when you take... Oh, because
Well, if you simplify square root of 8, it's 2 root 2.
Okay, I got you.
And the unusual step is that they don't usually, in other words, normally they would just take out a 2. In other words, they would leave this 4 times 2, and they would remove the 4 as a 2, and they wouldn't take the 2 out as a square root of 2. So that's what's unusual about this. The reason they do it is because they want to leave that behind, because that's something we're going to be able to integrate.
I see.
So they take out the entire number, which is root 8. Okay. Now, the reason we can integrate this is because that is equal to, by trig identity, in other words, this would actually be difficult to integrate.
Okay.
We don't have any way of integrating that, except it's a trig identity. It's this trig identity. And this trig identity is based on the following. Sine squared plus cosine squared equals 1. So therefore, cosine is equal to the square root of 1 minus sine squared of theta hold on. The half angle. Trying to figure out how they get from 1 minus cosine theta to this. I mean, I believe it, but I'm at a loss for trig identities at the moment to know how they get that. But let's accept that on faith for the moment. that the square root of 1 minus cosine theta is the same as the square root of 2 sine squared theta over 2. This probably comes from the half angle identity. Yeah, I seem to remember that the sine of theta over 2 is equal to the square root of 1 minus cosine theta all over 2. Something like that. That doesn't make sense either, because this still doesn't work, does it? But, well, like I said, let's just accept that on faith for the moment. Let me look at it a little bit. Maybe I can explain that a little better next time. And now, I love the algebra they do in these things, and they don't explain it, but it's so clever. Now we're going to remove this square root of 2. In other words, this becomes this. I think you can see that.
Yeah.
Now I'm going to take that square root of 2. There's still this outside the integral. I'm going to take this square root of 2 outside the integral. And now I have a 4.
Okay.
And the square root of this or rather, yeah, okay, so this becomes 4 times the integral of sine of theta over 2 d theta. In other words, if I take the square root of the sine squared, I get sine of theta over 2. And I know how to take the integral of sine of some number of theta. It's negative cosine divided by the derivative of the inside, which is 1/2. So it becomes 8 times negative cosine of theta over 2, evaluated between 0 and 2 pi.
Wait, where did the 8?
Well, the integral of sine of theta over 2, let's go back and review. The integral of sine of 5 theta is negative cosine of 5 theta divided by the derivative of the inside. So the integral of sine of 1/2 theta is negative cosine of 1/2 theta divided by 1/2, or 2 times negative cosine of theta over 2. And that's how this 4 turns into an 8.
Okay, so the integral of the sine of theta over 2 ends up being
negative cosine of theta over 2 times 2.
Okay, negative cosine of theta over 2.
In other words, this is what you have to remember, is that whenever you're taking the integrals of these transcendental functions, as long as theta is merely being multiplied by a constant, then the integral of this thing is, you can kind of use substitution and divide it by the derivative of the inside. In other words, this is what you need to remember, is that the integral of sine of c theta is negative cosine of c theta divided by c.
Okay.
Well, when we divide this by 1/2, it's the same as multiplying it by 2. And that's how your 4 becomes an 8. And we're still left with the negative cosine of theta over 2. We're going to evaluate it from 2 pi to 0. Well, at 2 pi, we're talking about negative 1. In other words, if I plug in 2 pi for theta, I got negative cosine of pi, which is a positive 1. So it's 8 times a positive 1 minus, when I plug in 0 for theta, I get negative 1. In other words, the cosine of 0 is positive 1, but it's a negative, so it's a minus 1.
We're not doing the divided by 2 part, or am I missing something?
Well, let's see. Here's what we did. Let me erase this here, because this was just instructional. This was not part of the problem.
Sure.
If we're trying to take the integral of sine of theta over 2 from alpha to beta, or from 0 to 2 pi, well, the integral of sine of theta over 2 is negative cosine of theta over 2 divided by 1/2, which is the same as multiplied by 2.
Right.
And we had a 4 multiplier in front of the integral sign. So that's where the 8 came from. Okay. That came from this. And we're evaluating it from 0 to 2 pi. In other words, we lost the integral sign at that step right there.
Okay.
Okay. And now it's a simple evaluation, and it becomes plus 1 plus another 1 times 8. So 16 is the length of that cardioid. Now, they do have a note or two here that is interesting. In the 5th step, where we took, remember when we took the square root of this, we said that that was equal to the square root of 2 times the sine of theta over 2. Well, in actuality, it's plus or minus that, right? In other words, if I take the square root of sine squared of theta, that's actually plus or minus sine theta. It's not always plus.
Oh, I see.
Minus sine theta is a legitimate answer also. So what they're doing is explaining to us how they were able to get rid of the plus or minus when they did this step here.
Okay.
Because technically that would be plus or minus. And they say it's legitimate to write that as opposed to this absolute value, which is the same as plus or minus.
Okay. Because
the sine of theta over 2 is always positive when theta is between 0 and 2 pi.
Oh, I see.
In other words, sine of theta is positive in the first and second quadrant. And so therefore, as long as theta is going from 0 to 2 pi, the sine of theta over 2 is always positive. It's always in the first or second quadrant. So we can ignore the absolute value. We can leave that out knowing that it's always positive.
It goes from 0 to 2 pi. Okay, I guess so.
Now, the very last note on this page is you can determine the reasonableness of this answer by comparing it with the circumference of a circle. For example, a circle of radius 5/2 has a circumference of 5 pi, which is approximately 15.7. And they're telling us that the length of this cardioid is 16. So how does it compare? In other words, the cardioid is this thing, and if we had a circle, the radius, we know that this is 4, so the radius of that circle, I'm not sure where they came up with 5/2. It seems to me a reasonable radius to check would be 2, right? In other words, if we know that this point on that cardioid is 0, -4, then you could say the radius of this cardioid is approximately 2.
Oh, I see.
If there was such a word as the radius of a cardioid.
Yeah, I see what you're saying.
So we could compare it to the radius of a circle of radius 2, which would be 4 pi. Oh, no, let's see, it would be pi r squared. It would be, 4 pi, and 4 pi is,
Well, it can't be squared. I don't think for the circumference. What's the formula for this?
Oh, you're right. It's 2 pi r.
Yeah.
2 pi r, and if r were 2, then that would be 4 pi. So it actually turns out that even though I was figuring the area, it turns out to be the same number as the circumference.
Oh, wow. Huh.
Only because 2 squared is the same as 2 times 2. Or, in other words, the circumference of the circle would be 4 pi, and the area of the circle would also be 4 pi. And 4 pi is 12 and change, which is interesting. You would expect the circumference of the circle to be larger, wouldn't you?
Yeah, that's what I would think too.
But the center is probably not exactly 2.
That makes sense too, yeah.
So I'm not sure that we can say that the circumference of a circle that was approximately the same as this cardioid would be greater or less than the circumference of the cardioid. And in fact, I'm not sure that you could even say that the circumference of the circle should be larger than the cardioid.
Yeah, maybe that's an area. But
when I do that, that's not longer than that.
Yeah, right. I mean, look, you think area should be less, but the circumference not necessarily, because
so I'm not sure we can say anything about whether the circumference of a circle should be less or greater than the arc length of the cardioid. The arc length of this cardioid ended up being 16. The circumference of a circle that would approximate it ended up being more like 13. So the circle must actually be a little smaller, like that. In other words, the circle doesn't trace the outside of the cardioid. In fact, and they said the circle of radius 5/2. Why they used 5/2, they don't say. But a circle of radius 5/2 would have a circumference of 15.7.
I see.
So I guess the explanation is, if I were to make a circle similar to this cardioid, it would not have a center right there. It would have a center over here. In other words, it would have a center closer to 5/2 than 2.
I see.
And it would look something like that. and it would have a circumference very close to the cardioid, 15.7 instead of 16.
Yeah, right. Makes sense.
But even still less.
Yeah, still right.
Yeah. All right, that's probably a good place to stop. And next up is the area of the surface of revolution. In other words, if you take a, say, the example that we're going to get to is Taurus.
Man, I can't even remember how to do the area of surface of revolution of anything at this point.
Well, if you take that circle,
Yeah.
which can be described with r equal cosine theta, in other words, that's a polar function,
Okay.
and if you rotate it about the y-axis, you get a donut, which I won't even begin to try to draw, but I think you can see that it would be a torus.
Oh, yeah.
It's called a pinched torus. And if we wanted the area of that donut, we would need the area, the surface area. In other words, we haven't gotten yet to volume.
Mm-hmm.
They've skipped right over volume.
Uh,
If we were doing rectilinear calculus, we would first figure out what the volume of that donut was when you rotate it about the y-axis. And then you would go to the next step, which would be to figure out the surface area of that donut. But this book appears to skip volume questions. In other words, volumes of objects that are polar equations rotated about one of the axes.
yeah.
They don't, not in this book do they get to that at all. There's only one subchapter left. Maybe they get to it there. I don't think so, though. But yeah, they talk about arc length, and they talk about area, and they talk about area of surface of revolution, but they don't talk about volume. Yes, the reason would be, if I try to draw that donut, wow, talk about something that's difficult to draw. I can't even begin to draw it.
Yeah.
But how would we figure out the volume of that thing? I'm sitting here trying to figure out whether you could break it up into disks or cylindrical shells, maybe. And I don't think this book that I have covers it even. So we may not get to that, although it may be in the next 5 chapters, which we'll do at some point in the future. In other words, I have, your book. I don't have the textbook for the next 5 chapters, but I have the file you sent me. So we can certainly do some of the next 5 chapters. The one I would very much like to do is the one that talks about 3D vectors. Only because I've always had difficulty with 3D vectors, and they're so real life. I mean, if you're going to fly a helicopter from one point to another at a certain speed, the only way to answer that problem is with 3D vectors and calculus, because speed is a calculus. Speed is a first derivative. So I want to get to at least the calculus of 3D vectors. And in fact, you and I have never really talked about 3D vectors, just in a non-calculus perspective. I run into it every now and then when I run into an IB student, because IB students get 3D vectors in high school, and they're the only ones that do.
Huh.
No other math student gets 3D vectors in high school. Not Calc AB, not Calc BC. I guess the girl I had who was a junior in Calc BC, when she got to her senior year, she took something called Beyond Calculus, and they got to 3D vectors.
Huh, okay.
So, but it's something that I definitely would like to cover, and we will. And then we've got probability and statistics also. In fact, I'm meeting with a new student tomorrow who is taking, it's not called probability and stats anymore. It's called discrete mathematics and statistics.
Huh.
In other words, they've replaced the word probability with discrete mathematics. But I asked her if she could bring me her textbook, and I'm going to take a picture of it and buy one online on eBay, and then I'll have a textbook for us to use. Because right now I don't have anything that would allow me to do probability and statistics with you. And I kind of feel like I want to do it, and you've expressed an interest in doing it, so it seems like it certainly should be in the future, whether it's the near-term future or the 6 months out, I'm not sure, but we'll go there eventually. Discrete mathematics, the difference between discrete mathematics and regular mathematics is, the short explanation is regular mathematics is continuous, discrete mathematics is integer mathematics.
Oh, I see. Okay, I see what you mean.
At least that's my understanding of the difference in the two words.
Okay.
And certainly, probability and infinite series. Infinite series are discrete mathematics because I goes 1, 2, 3, 4, 5, 6.
Oh, right, yeah.
It doesn't go 1, 1.1, 1.2. So infinite series are a part of discrete mathematics. And so is probability, although I don't quite know why it is. Because probability, you could have 1.64%.
Yeah.
But anyway. All right.
Well, thanks much, Dave.
All right. I will talk to you next time.
Okay. Thanks much. Talk to you soon.